Okie dokie. Today we're going to start by talking about, or we're going to start talking about chemical equilibrium, I suppose. Which is, what is that, chapter 15, I think, in our textbook. And so this one is going to be, it's such a big topic that we're going to have 3 more chapters on equilibrium itself. So 16 and 17 are also going to be on equilibrium, and then we're going to kind of skip one and then talk about thermodynamics, which is also going to be super heavy on the equilibrium side. So, yeah, it's going to be something we'll talk about for months. How exciting. But first, just wanted to know if there are any questions on kind of the either solution or kinetic stuff that any of you want to go over. I think we have some time, so if that's the case, let me know. Otherwise, we'll just start talking about equilibrium. So I'm going to first kind of do something that I don't normally do. I'm going to talk about history a bit here, just to kind of establish some things related to equilibrium. So back in like the, I don't know, 1800s or something, Industrial Revolution times, in Germany, they were trying to figure out a way to get nitrogen to become ammonia. So hydrogen is something easily kind of isolated. Nitrogen is pretty easily isolated, but trying to get them to turn into ammonia was problematic. And ammonia is a very important component of fertilizer, in that plants need ammonia or something similar, or nitrates, in order to get nitrogen. Plants cannot absorb nitrogen gas directly, despite the fact that we have tons of it in the atmosphere. You would need special bacteria to do this, or lightning is another way you can get ammonia to form. But, in the interest of trying to, mess with the world's population, having more humans, more food was needed, and so we needed to figure out how to get plants to grow better by making this ammonia. And so this was a troubling sort of task. And so eventually, in Germany, they did discover what was called the Haber process, which was getting these two to react in the presence of a catalyst. Of course, if we were to balance this, there you go. But something was interesting when they were to put these together. They found that the reaction would never go to completion. They would see, okay, we've got our hydrogen is going to be blue. Over the course of your reaction, they would see, okay, our hydrogen is going to flatline here if we have kind of the amount of hydrogen over time. And with, the nitrogen, they did the same thing. They're able to say, okay, you know what, we're going to also slow down. And then in terms of the ammonia being produced in purple, that would go up. But it would just kind of flatline out there. And they would still have some of this nitrogen and hydrogen left. And, kind of what they would do, didn't seem to really have a big effect on that. So this is being conducted at pretty high temperature, under pretty high pressure. So there wasn't really more they could do to figure out why they can't be getting all of the reactants to produce ammonia. And interestingly enough, they saw that if they just put ammonia into a sealed container, that the same thing would happen. They would actually end up decreasing their ammonia and increasing the other two until they would all kind of flatline. I guess these should be kind of mirror images, but whatever, I'm a terrible artist. You can deal with it. And so what they determined what must be happening is that, you've got your nitrogen and hydrogen producing ammonia, but at some point, you end up having the reverse reaction taking over, where you start breaking down your ammonia. And so they kind of developed this idea of reversible reactions, where you would instead write that you have something like this, where you have the reaction proceeding in both directions, eventually leading to this equilibrium. So these kind of arrows here indicate, I don't know how to spell indicate. Aha, there we go. Indicate reversibility. So we kind of talked about that in terms of the kinetics chapter we did with the reversibility of reactions. And we're going to see that, in fact, every reaction is technically reversible. Some of them will be kind of in this... I didn't spell reversibility right, did I? Indicate reversibility. Reversibility. While all reactions are technically reversible, we're going to see that we'll be able to kind of look at ones that are more reversible than others. And we typically indicate those with these kind of double arrows instead of a single arrow. And eventually, these will reach what is called an equilibrium. So we see that reversible reactions, though again, technically all reactions are reversible, just focusing on ones that are kind of more commonly reversible or more easily reversible, well, these will eventually reach equilibrium. And so equilibrium means two things. It means that your forward and reverse reaction rates are the same. So we did this yesterday when we were talking about those mechanisms where we had a slow second step and a fast reversible first step. We're going to see that the rates of reaction for forward and reverse will be happening equally. So that's kind of one kind of standard of equilibrium. And the other one is that the concentrations of all components do not change. So at some point, when you flatline here, you will be stuck at a certain concentration of whichever your reactant or product you're looking at. So all of your stuff is kind of in one state. So, you know, at some point you will reach, you know, some magic concentration at which you will no longer be changing your concentrations. So once it reaches it, that's it. Rates are happening at the same time, or rather the same magnitude. So they're, you know, it's being consumed as it is being produced equally. So concentration is not changing. So that's kind of how we define equilibrium here. Alrighty, and so we're going to see that we have some kind of nice thing called an equilibrium constant. Equilibrium constant. We're going to see there's a lot of different equilibrium constants. Define behavior at define behavior at equilibrium. And so we're going to see first off how to make an equilibrium constant. So here is our favorite generic reaction. Notice we're going to make this one a reversible reaction. We have Kc, which is going to be our equilibrium constant. Capital K sub C is going to be equal to your products over reactants. Or more specifically, it's going to be written like so, where we have each of our products raised to their respective stoichiometric coefficient over all of our reactants. And typically, we're going to be using molarity as our means of talking about the concentration. So technically, your units of equilibrium constant will depend on whatever reaction you write, as will your value. For example, let's say that we have here. Let's do our Haber process. If we do so, we're going to see that our equilibrium constant will be the products over the reactants. All of them raised to their respective powers. So if we were to look at this particular reaction, we're going to end up with units of molar to the negative second power. Just by looking at that, right? We would see we have 2 molarity components on top and 4 molarity components on the bottom. And so we'll end up with molarity to the negative second power. It's kind of bizarre. So the units of this are kind of not so important because they will just completely vary based on whatever your reaction is. And so we're going to take a look at a few more examples here. But we can mess with things here. So yeah, notice if we take, for example, this reaction, we can come up with an equilibrium constant for it as well. And we're going to see that this would have units of molar to the negative 4. So it just depends on how you write your reaction. So very often we kind of just omit the units for the equilibrium constant, for this being one of the reasons. We're going to see that we use equilibrium kind of to talk about a couple of different things, one of them being thermodynamics, which we'll talk about far later on in the course. But thermodynamics, we don't really talk about molarity anymore. We talk about the activity of various components in a reaction, and those have different units. So very often, since we would still be using Kc, we just kind of forget the units, just throw them out. So there you go. You don't have to worry about the units for this. That's the whole point, I guess. Just so you know that if you are going to be plugging in values for this, for right now, use molarity. So don't use millimolar or something like that. Just use molarity. Let's see. What else can we do with this? If, for our Haber process, the equilibrium constant is, I think it's like 6 point something. Here, let's find out. Haber process equilibrium constant. I think it's something to the 10 to the negative 2 or something like that. Whatever, let's find out a value for one so we can actually work with it. Let's see. Aha! I guess it's 10 to the negative 3. Whatever. Oh, this is a different reaction. Haber process. Hi, here it is. What, really? Oh, I lied to you all. It's something really big. For the reaction as written here. Apparently, I guess I was thinking of it as at a different temperature, but oh well, who cares? Here's an equilibrium constant. We don't care about the units. It's very important that we do indicate your reaction for talking about the equilibrium constant. For example, we can figure out what the values are going to be of each of these components. Let's say we have, I don't know, let's see what we can do to make this work. Let's say we have 1.6 molar of this, 0.002 molar of that. Let's figure out what nitrogen is going to be. Let's do that at equilibrium. By doing that, we can just plug in our equilibrium constant. I don't know why I'm using brackets. And then we would put this guy here at the bottom. Oh gosh, why did I choose such a complicated one? Kevin, calculate this for me. I don't want to do it. I'll do it. 1.6 times 1.6 divided by 2.7 times 10 to the 8th divided by 0.002 to the third power. What do I get? Something reasonable, perhaps? I guess so. 1.19 molar. Hooray. We're able to figure that out. If we take these values and put them in that second equilibrium expression we did, where we had the doubling of the coefficients, let's take a look at what that would look like. If we plugged in everything kind of squared here, we're going to end up squaring our equilibrium constant, right? Just mathematically speaking. Okay, awesome. I'm glad we got the same thing. Right, if we square our entire thing, we're going to square our constant. Doing that, we get whatever the heck that's going to be. 2.7 times 10 to the positive 8th squared. Okay. We get 7.29 times 10 to the 16th. So we're going to see your equilibrium constant will also depend on your reaction. Whatever reaction you end up writing, you will end up with a different equilibrium constant, even though if it's the same process. So we can calculate it if we really wanted to. If we wanted to take that number, we could calculate the concentration of our mystery nitrogen gas, just like before. We would end up calculating that it would still be the same value that we had before, 1.19. So, hooray. Point of all this is that the concentrations of all of our components are constant at equilibrium. At a certain temperature. We're going to see that the temperature, of course, as we know, affects the rates of reactions, and so that's going to mess with our equilibrium constant. So equilibrium constants are determined at a particular temperature. And so we're going to see how temperature affects equilibrium constant later on, but for right now, just understand that it will change. But notice that while Kc, while Kc can change based on the reaction written, the concentrations are still the same. Concentrations are still the same. I guess concentration is. I can't really say concentrations are here. There we go. The concentrations are still going to be the same. So we would end up just changing our constant depending on what reaction we write. And so, however, the concentrations of those particular components would not change. So if you decide to change your reactions, coefficients by doubling it or tripling it or whatever, you still end up with the same concentrations for your components. Hooray. questions so far? Just so we know, when we are generating equilibrium expressions, that's the, like nitrogen to the first power and hydrogen to the third power. That's an equilibrium expression. We omit solids and liquids. Because those ones will have very different activities compared to things that are in solution. These also don't really have concentrations necessarily. So pure solids and liquids, if you throw a rock into your reaction, you would not be including your rock in its equilibrium expression. We just include aqueous and gaseous components. When we're dealing with those. Specifically, we're going to talk about a special case for gases, but we'll have a special equilibrium constant for them as well. So we can do with that. First, though, let's work with some of these equilibrium constants. What we can do with it. So we've already seen that we can determine the equilibrium concentration, right? We can determine equilibrium concentration of a particular component. We can definitely do that. That'll be very helpful for us. That's kind of the biggest use for it, I suppose, is determining the equilibrium concentration of something. We can do that either in a number of ways. Like for that first couple of examples, we were given the concentration of the other components at equilibrium. But we're going to see that we can also have initial concentrations of something. So let's go ahead and see what that might look like. So suppose we mix 10 molar hydrogen and 5 molar nitrogen. We can figure out what the equilibrium concentrations are going to be for all of these. It's going to be kind of hairy with this particular example. We might have to use Wolfram Alpha for us or something. Let's see. Let me just get that. Let me get that ready because we're going to need it. How exciting. So we would do this by generating what is called an ice table, where you would take your reaction and write out its equation as so. You would have your initial, that's the I, your change, and your equilibrium concentrations. We're going to see that if we start with 5 molar and 10 molar, start with nothing for there. As this reaction progresses, we're going to see that we're going to use up some amount of nitrogen, and we're going to use up 3 times the amount of hydrogen, right? So for every bit of hydrogen there, or nitrogen, we're going to use 3 times as much hydrogen. That's what the stoichiometry is all about. And in doing so, we're going to generate 2 kind of X's of ammonia. And so at equilibrium, we would have the following concentrations. If we take our, what was it, value from before? 2.7 times 10 to the 8th. This was equal to ammonia squared, hydrogen cubed, and nitrogen, right? We plug all this stuff in. Five minus x, and then 10 minus 3x cubed. Look at this disaster that we're going to have. But technically, we can solve for x. I think this one we're going to get all these different values. It's going to be horrible. It's a really terrible example to use for this. But suffice it to say, Wolfram Alpha can probably solve this for us. I can't. I do not have the math skills necessary to solve for x when we have all the, x to the 4th going on here. But if we solve for x, we can figure out what that concentration is going to be. Let's see if we can do that with Wolfram Alpha. Okay, we can do this. Solve for x calculator. Here's our equation. What would our equation be? I guess we have to put all of these things. Okay, let's go ahead and do this, and we'll use Wolfram Alpha to figure it out for us. So let's go ahead and start by moving everything to, having it all on one side or something where we could have, our x is equal to 0. So we know that we're going to have, oh my gosh, this is going to be so complicated. I don't know why I chose this example. We'll deal with it. Oh my gosh. Oh, yikes. I really dug myself. So let's see if we can just plug it all in as written. 2.7 times 10 to the 8th times 5 minus x times 10 minus 3x cubed minus 4x squared equals 0. Please solve it. Let's see. Did we get an answer? Aha! Okay, so doing this nonsense, magically we did get an answer, which is lovely. We have a couple of values here. Plugging this in to Wolfram Alpha, we get all these values out. I'm going to just say these ones, of course, should definitely be ignored because we're not going to be dealing with our imaginary numbers. Apparently 5 is an answer here, or is 3.33. Obviously 5 can't be an answer. Let's look at why, but this is one way to solve this sort of thing. Hopefully the examples that we will have will be like quadratics. You can use the quadratic equation to solve them, or there's going to be nice approximations we can do. Suffice it to say, let's go ahead and try that 3.33 stuff out there. If we do that, we can go ahead and plug all this stuff into our table. So we saw that for nitrogen, its equilibrium concentration would be 5 minus 3.33, which would be 1.67 molar. That is the amount of nitrogen we would end up having at equilibrium. In this case, it looks like we're going to be out of hydrogen pretty much. Some small amount left, just based on our sig figs. And then for ammonia, we would end up seeing that our concentration would be 2 times 3.33, which would be 6.66 molar for our ammonia. So yeah, Wolfram Alpha will be your friend if you're ever dealing with more complex ones like this. Do you all see, by the way, why I got rid of 5 as a potential answer, even though that the program did spit that out at us as an answer for x? it will not work because, of course, we can't end up with a negative value for concentration. If we did 10 minus 15, we would end up with negative 5 molar for hydrogen. That is not a reasonable answer, so we can kind of dismiss that value as being of use to us. So that's what we would end up with for this particular example. You know, there's a couple of things we can talk about Kc that may be of help for us as well. That can help kind of explain why we got such a small value for hydrogen. If your value of Kc is much bigger than 1, your equilibrium will favor the products. That means you're going to end up using up a lot of your reactants and you're going to have a large proportion of products. And that makes sense, right? Because if Kc is products over reactants, and that's bigger than 1, that means you have more products than reactants, right? On the other hand, if Kc is less than 1, then it favors the reactants. You end up having more reactants than you do products. And remember, though, again, Kc all depends on the way you write your reaction. So if you end up writing your reaction like this, we saw Kc for this would be 2.7 times 10 to the 8th. If we were to write the reverse reaction instead, we've already discussed that as written above, that it favors the products. So if we write the reverse, it's going to have to favor the reactants, right? I mean, it's just switching things around. And that would be, therefore, 1 over the other Kc. Since as written, our Kc would be the opposite of the one that we originally had, the inverse of it. Since flipping the reaction, we will just inverse our equilibrium constant. And so as written, Kc is going to be, let's just do it real quick, 1 over 2.7 times 10 to the 8th. In this case, it's 3.70 times 10 to the negative 9. So this information we're going to see tells us exactly the same thing. But it really, again, just shows that Kc depends heavily on the way that you write your reaction. So as written on the top, we see it favors the products, which is ammonia, and we'll be able to calculate our concentrations based on that. If we look at the bottom reaction, we can see it heavily favors the reactants, which makes sense again because we've already demonstrated we're going to have more ammonia through this process. As so, we can see that the equilibrium constant will be much smaller than 1 as a result. All right. Tons of information so far. Hopefully none of it is too crazy. Hopefully the craziest thing was that horrible set of equation, or horrible equation with x to the 4th in there that we had to deal with, but we got through that. I don't expect on your homework that you're going to have anything that deals with more than x squared. I guess we should throw that out there. You know, if you end up with, if you have x squared in your equation, hopefully we know how to solve for x with that. If you can arrange your equation as such, let's see, negative b plus or minus radical b squared minus 4ac over 2a. Is that right? I think it is. I mean, how many times did we say this in middle school, right? Or high school? If you have an equation like this, you may need to use the quadratic equation, but I would definitely recommend using the internet to solve it for you. This is not algebra class, it is chemistry class. I do not particularly care if you can use the quadratic equation or not. But there it is. For those of you who want to do things manually, go right ahead. Otherwise, just use Wolfram Alpha. I guess I should throw that out there so you can see what that looks like. Okay, here is, where are we here? Yeah. If you just go to wolframalpha.com, you know, just search this solve for x calculator. You can plug in your equation. Let's say, you know, I have 3x squared plus, I don't know, 12.8x minus 22 equals 0, whatever. It'll compute it for you. Oops. And in this case, it's given, oh God, we've got some really crazy numbers because I just made these up, but it'll compute it for you in a new window, and you'll be able to see it, see what the values are. I guess I can show you what that looks like. That's the one I get out of this. When I do that, I get, this is my value here. I don't know what the heck these mean, but there's your x value. So again, don't be like me, don't just make up random equations like I do, but that is how you would use this to solve for x if you had a particular problem. So yeah, here, let's make it positive. That may make things nicer for us. Let's see what we get out of that one. Oh no, we get imaginary numbers. Never mind. Okay, that equation never happened. So, but that's the idea. Same thing. Just use Wolfram Alpha to figure it out for you. Or you can use your quadratic equation. Cool. So again, not a math class. I don't really care if you know how to do this math or not. I care about the chemistry. Hooray! Alrighty. Any questions on that stuff so far? If not, we'll start talking about another equilibrium constant we have. Alrighty. We have Kp. We know that for gases, the pressure of the gas is proportional to the number of moles, right? And thankfully, since we know that all gases behave somewhat the same way, we can kind of just use our pressures instead of having to calculate molarity for this. So for, let's see, what's our favorite? Oh, I know, we have our absolute favorite reaction of all time, which I have now made into an equilibrium reaction. Same thing from before. We can say that Kp would be equal to the pressure of CO2 times the pressure of NO over the pressure of NO2 and the pressure of CO. I really should have chosen one that has exponents, but if we had it, here, let's do it. Let's put 2's in front of everything. We can do that. It's just like the equilibrium constant Kc, except we're using pressure instead of molarity, instead of concentration, which is what the C stood for. Now we're using pressure. So we can figure it out in terms of pressure units instead. So we could use atmospheres or millimeters of mercury, whatever we want, as long as we're using the same units, we can figure that out. How exciting. Woohoo. So Kp would use exactly the same way as if you were using Kc, but you would just use pressures instead. Hooray. So we could totally do that if we had our same reaction from before, or here, let's do another one. Probably not an equilibrium reaction, but let's pretend it is. We could say Kp for this reaction would be the pressure of water squared over the pressure of hydrogen squared times the pressure of oxygen, whatever those happen to be. So just like before, it's exactly the same thing, we're just changing the unit. Doesn't really have any impact on our stuff so far. However, we can relate this stuff to Kc. We could talk about molarity of gases, right? That's just N over V. Remember that molarity is just moles per volume, moles per liter, right? Same thing. If we look at what pressure is equal to, nRT over V, right? Notice that this part contains molarity. N over V is the same thing as molarity, moles per liter, just like we have always done with our gas laws. And so we could say instead, we could say, okay, Kp was the pressure of water, pressure of hydrogen, pressure of oxygen. We could say that that's N of water times RT squared. Oh my gosh, this is going to take up so much room. And then, oh god. This is, why am I doing it this way? I always choose the most complicated problems to give you guys. Someone needs to put a stop to that. So, and that would be for oxygen. Oh, thank goodness this one does not have whatever. Notice that this is molarity of, I guess I can actually just use concentration. We have the concentration of hydrogen times RT squared, and then we have our concentration of oxygen times RT as well. Hooray! So, we know that Kc was all that crap minus the RTs, right? Kc for this reaction would be we would just use the concentrations instead. So remember, this is Kp, is all that stuff. Do we see how we can possibly relate these two? Relating Kp to Kc? Mathematically speaking? Which, we can just put that. It's going to be Kp times RT. But what's tricky here is we have an exponent thing to deal with. So notice in the top part we have RT squared. In the denominator we have RT cubed. We're going to see that we have basically something called delta N, which will just be the difference of moles of gas. The gas coefficients. In this case we have, and it's always going to be products minus reactants. So in this case, it's going to be -1. remember that we have 2 waters, and here we have 2 moles of each gas there. So in this case, we're going to see that our delta N would be -1. So that is how we can relate Kc to Kp. Very exciting stuff. So for this reaction, delta N equals -1. So if our Kc or Kp, let's just do an example, I guess. I'm going to make up a number. Let's see, this reaction should definitely favor the product. So let's say we have 1.61 times 10 to the 7th. I don't know. Let's just throw that out there. We can see what the concentration equilibrium constant would be for this reaction. Same reaction as before. So Kc equals Kp times RT to the -1st power in this case. Or let's just say delta N. And so that's going to be 1.61 times 10 to the 7th. I guess I have to put RT in parentheses, so we know that the exponent is put to both of those, times our gas constant. Ooh, what temperature should we have? I don't know, 300. We can do that. And so doing so, here we go. So we're just going to divide it by instead. So 1.61 times 10 to the 7th divided by R divided by 300. Doing this, I get 6.54 times 10 to the 5th. Hooray. Very exciting. Kevin, let me know if you get the same thing. But that's how we can relate those two constants to each other. So, you know, I'm sure you're all very thrilled of being able to convert Kp to Kc. As you can imagine, it should have quite a few applications. Okay, I'm lying. I don't really see the point. But it is still valuable to be able to do so because I can ask you problems on it. And it's just a way of, again, relating your knowledge of various chemical concepts together. So basically we're just employing the gas law, ideal gas law, to convert to this. Okay, looks like the same thing I got, Kevin. Awesome. So I just had rounded stuff, I guess, and scientific notation it. Coolio. Alrighty. Any questions on this sort of thing? You can use Kp exactly as you would Kc. You know, we can solve for x doing that sort of nonsense as well. You know, we could totally make it work. Here, let's do an example maybe. And this one will actually be not too bad, I think. Yeah. This one will actually work. Let's take our absolute favorite reaction. And I'm going to say that Kp for this is, what shall we say it is? I don't know, 6.22 times 10 to the 4th. I don't know. Making up numbers. Always goes well for me, right? Let's see if we start with 1 atmosphere of each of our reactants. Let's see what we'll end up getting. So let's say we're going to put all those two together in our container. And I don't know where I'm going to move this thing. Let's move it down, actually. Somewhere down there. Whatever. We're going to not start with any of our products. And let's go ahead and do our ice. Let's see what we can figure out about the concentrations of all these things at equilibrium. So we're going to use up some of our reactants. We're going to make our products. we end up with those as our equilibrium concentrations. Putting together our expression, pressure of each one, of course, we end up getting x squared over 1 minus x squared. This one we can actually solve. Hooray! So we get x squared will equal 6.22 times 10 to the fourth times, oh gosh, 1 minus x squared. Let's see, that's x squared minus 2x plus 1. Yeah. Solving for this. Oh, look, we're even getting rid of our x squared, isn't that? Oh, no, we can't get rid of our x squared. Oh, well. Doing that, we get... Let's just figure this out. Oh, that's annoying. Oh, well. Into Wolfram Alpha we go. Let's go ahead and pop that open. Okay, here we go. Let's type it in. Or you can use your quadratic equation, but that's going to be tough because we have this big ol' exponent here. 6.22 times 10 to the fourth. Boy. Times x squared minus 2x plus 1. So much typing because I don't want to actually calculate it myself. Why would it actually give me like numerical values? Like it's giving these horrible like 10 times this thing over that thing. Like how annoying. Okay, let's see what I have to actually calculate these. That's quite silly. So 10 times 6220 minus 622 to the half power. All that divided by 62119. I get x to be 0.997, I guess. Again, something that I've just used Wolfram Alpha to do because I don't feel like calculating these things myself. Let's see if this makes sense. We end up having the pressure of our reactants will end up being 0.003 atmospheres. The pressure of our products will equal 0.997 atmospheres. If we look at these numbers, it looks like our equilibrium favors the products. We can just see we have quite a few more products than we do reactants. And if we look at our constant, we saw that that's much bigger than 1. We already knew that this reaction favored the products, but now we kind of have proof that it does. So if we had made this constant a little bit more like not so big, if we made it just times 10 to the 2 or something, we would get more reasonable answers instead. So, you know, it just kind of depends. If you have a really big equilibrium constant, you're going to end up with large concentration of your products or pressure of your products, as we have here. And if it's really small, you'll end up having more concentration of your reactants or pressure of your reactants, depending on what you're doing. So, hooray. If we wanted, we could also solve for the concentration of these instead, but we would need the temperature to figure that out. Okay. Exciting. Have we had enough equilibrium for one day? I think so. Wow. How exciting. If there's any questions, of course, you can put them out there. we'll continue this. Otherwise, next week we'll start with some more examples, perhaps, and we'll talk about more stuff related to equilibrium as we go on. So, cool. Yeah, definitely enough equilibrium, right? So, honors people, I'll see you tomorrow. Everyone else, I'll see you Monday. Next week, we will have a class on Thursday for everybody, so we can review all of the stuff that we want. You do have kinetics stuff to be doing. That's due next week. I'll probably have some equilibrium stuff that I'll be putting out next week as well. So I would start working on that kinetic stuff so you don't get swamped with too much. Definitely the kinetics is fewer problems than I had for solutions, and I'm totally regretting giving you that much for solutions because I mean, you already know how long it took you guys, but I did a couple hours of it last night, and where am I on this? I am somewhere in the 60s. So the answer key is forthcoming, but yeah, I have definitely gone way overboard with that homework, so I apologize. What I'll do is I'll make it worth more points to you guys, so you know, it'll be more valuable for you to have done all that work. So yeah, I guess in just reading the problems, I was like, oh, this seems like a good idea. This one looks good. This one looks good. And narrator would say it was not good. It was not a good choice. So I apologize. But I suppose that doesn't really mean much, right? You've already had to suffer through it. So, but think of how good you are at solutions now. So, yeah. Alrighty. There we go. See you guys next week. Take care.